Thank you, and let me thank the organizers for having me here. This work has been done at the Center for Earth Sciences at IISc Bangalore, and I'm going to present something which I did with my former PhD student, Swarandeep Sahu, who has now graduated. So I am essentially presenting on his behalf. So all of us know that the Earth has a magnetic field which has a north-south polarity. So this is a snapshot of the present-day magnetic field of Earth. And the horizontal axis is the longitude, and the vertical axis is the latitude. And what is striking in this magnetic field is that on top of the dipole field, there is a signature of non-axis symmetry, in the sense that there are some preferred longitudes where the Earth's magnetic field is concentrated, and these are at relatively high latitudes, and they happen to be sitting beneath Canada as well as beneath Siberia in the present-day field. And there is also a matching magnetic flux patch in the southern hemisphere. And it has been a long time since people proposed that this preferred orientation of the magnetic field has got to do with the interaction between the core and the mantle. And this interaction gives rise to an inhomogeneity in core convection. And we find that the patches beneath Canada are relatively unstable, and sometimes they break into two. And you might have read in the media recently that the Earth's magnetic north is actually migrating towards Siberia from Canada, which means that this region of the magnetic flux has weakened considerably, and this region has strengthened. And so we thought that it is essential to understand the difference in the flow patterns which might be happening in the Earth's core that would give rise to such a dichotomy between the east and the west hemispheres of the Earth. Now, to tackle this problem, we came up with a simplified model of the Earth's core, where we have an annulus, which is made up of two concentric cylinders, and we mimicked the seismic shear wave velocity variation in the lower mantle as a boundary condition for the top of the core. So this is what we obtained from observations. So there are regions in the mantle which are relatively warm, and regions in the mantle which are relatively cool, and these influence the convection pattern in the core that is lying underneath the mantle. And motivated by this pattern of heat flux at the boundary between the core and the mantle, we constructed a simplified heat flux distribution on the surface of this annulus, and examined what variation in convection that this would produce. So this is the experimental setup that we used to understand this problem. As I said, this is a cylindrical annulus which is filled with water, and the inside is made of aluminum and kept isothermal. And we have a transparent wall for this test cell so that we can shine a laser and use a camera and understand the flow patterns using particle image velocimetry, PIV. And the entire setup rotates at a velocity of 300 revolutions per minute. And the radius ratio of the setup is 0.36, which is approximately the radius ratio between the inner core and the outer and the core mantle boundary of the Earth. So in this experiment, we use centrifugal acceleration to mimic gravity and use a reversed temperature gradient. So gravity is not inward as in Earth, it is outward, and therefore the heating also has to be reversed. so that we obtain buoyancy, and the rotational Froude number, which is the ratio of the centrifugal acceleration to Earth's gravity, is of order 10, so that Earth's gravity can be safely ignored in this experiment, and it's centrifugal acceleration which essentially controls the dynamics. And this, as I said, we have a temperature difference between the inner and the outer cylinders, and the experiment is designed to obtain the response of rotating convection to a variation in the outer boundary heat flux. And we quantify this variation through this parameter Q star, which is the ratio of the azimuthal variation in heat flux to the mean heat flux at the outer boundary, and it varies in the range of 0 to 2. Now, this is what we have deduced from the seismic shear wave velocity variation in the Earth, and this is what we have set up in the experiment. So we can see that we have tried to mimic with opposite sign the heat fluxes beneath Canada and Siberia as they exist on the equator of Earth, and these two regions, the heat flux are kept approximately equal. They represent the Pacific and Central Africa. Now, this compares the scaled up heat flux distribution at the boundary in the experiment with what we have in real Earth, and we can see that although we have equal area sectors of heating and cooling, it approximately mimics what we expect at the core mantle boundary of the Earth. One advantage of using a cylindrical annulus over a spherical annulus in the experiment is that an important property of rotating fluids, which is called geostrophy, is approximately satisfied. And this happens even in strongly driven convection in a cylindrical annulus. And this, we believe, is an important property that in rapidly rotating planetary cores. And that is satisfied in the experiment because the variation in the temperature, azimuthal temperature, is entirely in the horizontal direction, which is azimuthal, and there is hardly any axial variation in temperature. So this term is negligible. So the Z vorticity is approximately invariant along the rotation axis. And this property is commonly known as quasi-geostrophy. And we are able to reach this regime through the experiment, which is why this experiment has a distinct advantage over an equivalent spherical shell experiment. Now, these are the convection patterns that we got by doing this experiment over a series of Rayleigh numbers. You can see that convection first sets in beneath Canada, and the reason for that is the Canadian heat flux is the largest. It provides the largest temperature difference between the inner and the outer boundary. The convection first sets in there, and convection gets stronger there, and at some point beneath Siberia also convection starts. And as the Rayleigh number for convection is increased, we find that convection breaks down beneath Canada, and then convection becomes coherent beneath Siberia. So what we see is that the patterns of convection that the Canadian region experiences is also followed by the Siberian region, except that it is displaced over a higher range of Rayleigh numbers. So the dominant structure of convection is that of a cyclone-anticyclone vortex pair. So what I have shown here is the Z vorticity with arrows of radial velocity superposed. And we find that the predominant structure of convection in strongly driven states is that we have an isolated downwelling, a coherent cyclone-anticyclone vortex pair beneath Asia, essentially Siberia, and broken convection beneath Canada, which means that this convection has a long-lived nature, whereas this convection has a predominantly, relatively transient nature. And this is what we expect in the Earth. because this pattern of convection is experienced in subfigures D and E over a wide range of the Rayleigh numbers. And if we crank up the Rayleigh number to a very high value, of course, the entire cylindrical annulus is homogenized in convection. But we believe that this is the regime that the Earth's core likely operates in. So to summarize, if I plot the radial velocity in the experiment and compare it with a spherical shell calculation, which are extremely expensive compared to the experiment has taken time to build, but once you build the experiment, it's very quick to actually get these runs out. So what we see is initially at very low Rayleigh number, we have a predominant downwelling, a radially inward flow beneath Canada. But as I increase the Rayleigh number, this actually switches over to the Siberian region. And with this, as I said, is what we expect to occur in the Earth's interior. And this is what we see in spherical shell calculations at supercritical Rayleigh numbers. So initially, it begins with a Canadian convection, and the pattern of convection suddenly switches over to the Siberian region as the Rayleigh number increases. So there is a broad qualitative agreement between what we see in the experiment and what we see in a very expensive numerical calculation. Now, what are the implications of this study? So this will be my last slide for the Earth. The implications are that at relatively weak convection, as we see here, the magnetic flux is concentrated predominantly in the Western hemisphere because convection is coherent there. And as we increase the Rayleigh number, both the East and West have some parity in terms of the magnetic field strength. And this is what most dynamo models have shown. And if I increase the Rayleigh number even further, what happens is that the Canadian patch weakens considerably, and the bulk of the magnetic flux is concentrated beneath Siberia. And this is precisely in the present day magnetic field that there is a preference for the magnetic north towards the east relative to the west. And we think it is a combination of the heterogeneity of the lower mantle coupled with strongly driven convection in the core, subject to the condition of approximate geostrophy, actually causes this distinct behavior of the Earth's magnetic field. Thank you. Thank you for your attention.
Questions? So, can you explain the analogy between magnetic flux and temperature?
Yes. So what happens is when there is a cold region of the lower mantle, it will actually let more heat out from the core. More heat will be extracted from the core. And that is where we expect convection to be dominant. And where convection is dominant, it will try to concentrate magnetic flux because it works through the magnetic induction equation. So we will say, in general, cooler regions of the mantle promote concentration of magnetic flux. And warmer regions will actually suppress the extraction of heat from the core to the mantle, and there we expect to see weaker magnetic flux. So that is in general supported by dynamo models, and that is what we see in this study as well. Broadly, that is the explanation. Yeah, I mean, it all depends on the layer that lies over, because that is, so the lateral variation there determines how much heat is extracted. Suppose there is no such lateral variation, heat will be uniformly extracted everywhere. In such cases, you don't get to see these kind of flux concentrations. So if one sees flux concentrations, I would imagine that there is a lateral variation in the heat that is actually extracted from the layer underneath. So yes.
The statement that you made, that the advantage of a cylindrical experimental setup, the annular cylindrical
Yes.
experimental setup over a spherical one,
Yeah.
is the quasi-geostrophy.
Yes.
I didn't quite understand why a spherical one would not maintain
Yes.
quasi-geostrophy.
Yeah, because a spherical one has sloping end walls. Okay, and it is, you have to rotate the spherical shell really fast to actually get a z vorticity which is invariant along the rotation axis because of that. And the radius of a sphere is different from the radius of a cylinder. Okay? So buoyancy in a spherical shell acts in the radial direction. And when that happens, you will have an axial variation in temperature naturally coming out of the system. And when that happens, I showed one term on the right hand side where the axial variation temperature is small in a cylindrical annulus. That term will be substantial in a spherical annulus provided the rotation rate is really rapid. Okay? So we can obtain this state at a relatively weak rotation in a cylindrical annulus.
Questions? If not, let us thank Professor Sreenivasan again for this wonderful talk.